In this video, we are going to look at the theoretical definition of stress and some other theoretical topics related to stress. So, let us consider a body which is subjected to external loads, and let us say Q is the point where we would like to calculate the stress. So, the first thing we will do is we will section the body. It should pass through the point through which we want to calculate the stress. So, we will keep the flesh colored part and we will discard the blue color part. Now, let us focus our attention on the part that we have retained for analysis. Because there are applied loads, there are going to be reactions. But before that, let the outward normal of the section that we have created be vector n. And for convenience, let this vector n be parallel to the x-axis. So, we are going to define our coordinate axis system such that the x-axis passes through the outward normal of the cut plane. Now, in the face that we are interested in, there are going to be various internal forces, but we are only interested in the point Q. At point Q, the sum of all the internal reactions could be denoted by a vector delta F, which might or might not be parallel to vector n. So, area delta A is the point Q where we are interested in. It is acted on upon by a force delta F. Okay, since it is a point, delta A is tending to 0. Now, we will focus our attention completely on this point Q. Area is delta A, force is delta F. It is at some angle with respect to the outward normal n, and keep in mind that the outward normal n is parallel to the x-axis. Now, we have decomposed the force delta F into the three components: delta Fx, which is the component of the force delta F in the x-axis, and similarly we have delta Fy and delta Fz. The figure has been repeated here. Now, stress components at point Q are defined as limits of internal force over area ratio as the elemental area shrinks to 0, or mathematically sigma xx is defined as limit A tend to 0 delta Fx by A. Tau xy is defined as delta Fy divided by delta A such that delta A is tending to 0. Similarly, tau xz is defined as delta Fz divided by delta A tends to 0. So, sigma xx is the normal stress. Normal stress means that the direction of the outward normal, that is n, which is parallel to the x-axis, is the same as the direction of the force, that is delta Fx. Tau xy and tau xz are the shear stresses. The outward normal of the area is along x, but the force is along y and z respectively. So, they are shear stresses. So, this is the sign convention that we normally use. Tau, you write sigma or tau depending on whether it is normal or shear stress. The first subscript will give you the direction of the plane or the outward normal of the cross section that you have considered. The second letter gives you the stress, the direction of the stress. So, now look at this figure and try to figure out which component of stress is shown by this arrow. The outward normal is the y, and the force is parallel to the x direction. So, this arrow is depicting the stress component tau yx. Just like we have chose a section and such that the outward normal was parallel to the x-axis, we could actually have done it 3 times, once where the outward normal was parallel to the x-axis, y and z respectively, and instead of a cross section, we would actually get a cube with 3 components of stress along each plane. If I make a cross section such that the x-axis is parallel to my outward normal, Then the three components of stress on that cuboid are sigma xx, tau xz and tau xy. Similarly, on the y is sigma yy, tau yx, tau yz, and on the z axis you have sigma zz, tau zy and tau zx. So there are actually 9 components of stress we are getting. They can be arranged in a 3 by 3 matrix like this. This is because stress is a second order tensor. When we say stress is a second order tensor, it means that both the direction of the force, that whether is it the x component or the y component or the z component of the force, that is important. Also the direction of the outward normal of the cross section is also important. If you recall, area is also a vector. So stress is equal to force by area. Force is a vector, area is a vector. When a quantity depends on two direction components, we call it second order tensor. By that logic, a vector depends on one direction component. So we can also call it first order tensor. A scalar which has no directional dependence is actually a zeroth order tensor. So to recall, tau xy, if somebody writes, it means that it is shear. We are gathering this information by tau. The plane is along the plus x axis and the force points in the y direction. So now look at this figure and can you tell me what is the component of stress? The outward normal of the face on which this force is acting is x. The force is also passing through x. So this is sigma xx. Similarly, in the second figure, the outward normal is the x, but the force is passing through z direction. So this is tau xz. And finally, it is tau zy. Now, we found out that there are 9 components of stress, that stress can be shown as a 3 by 3 matrix. Let us try to find out if there is some relationship between the two. Consider a body which is, for simplicity, let's do a two-dimensional analysis. It is subjected to sigma x, sigma xx, sigma yy, tau yx, tau xy. Let us take moment about the centroid of my cuboid. Sigma xx, sigma yy pass through the centroid, so we don't need to consider that. I have tau yx into 2 times delta I, that is the top area and the bottom area, is equal to 2xy into delta I. The area on the right, area on the left, so I have 2. This tells me that tau yx is equal to tau xy. So what this tells me is that the cross shear terms are equal. So instead of a 3 by 3 matrix which has 9 components, I actually now know that my 3 by 3 matrix is actually symmetric. So to completely determine the stress at a point, we need to calculate 6 quantities. So 6 components are needed to completely define the state of stress at a point. Now, I think most of you by now have an appreciation that we are going to use the concepts of stress to design different parts. Now, every material has some maximum stress after which it fails. So, there is no material in the world which can take infinite amount of load. So, let us say that the maximum stress at which my material is going to fail is ultimate stress. Okay. Under normal conditions, the maximum stress that a material will encounter is going to be significantly lower than the ultimate stress. This is because as a designer, you are not going to take undue risk. So you are going to do all your calculations based on the maximum load that a material is going to get, but your material is still not going to fail. The maximum stress that a material will encounter is designated by allowable stress. This is something that the designer has to calculate. And therefore, we come to the definition of what is known as factor of safety. Factor of safety is the ratio of ultimate stress divided by allowable stress. For example, imagine that I have a material which fails if the stress is 100 megapascal. But while designing it, I designed my part in such a way that the maximum stress that that part get is only 50 megapascal. So my factor of safety is 2. It means that even if the load was doubled, only then my material would start failing. Factor of safety is incorporated to account for various uncertainties during real life. For example, there might be some machining errors. You want a piece which is, let's say, 2 by 4 millimeter cross section, but somehow due to machining it is 1.9 by 3.8 millimeters. Or the load that you were expecting was superseded by 10% due to reckless use by the end user. And there are various other factors. So to account for all the factors that we cannot be 100% sure about, we will use this factor of safety. In some engineering terms, factor of safety is also known as factor of ignorance, because this factor is introduced because we are ignorant about certain things. Finalizing the factor of safety for an equipment is very difficult because it will depend on a large number of considerations, and usually this decision is taken by a very experienced engineer. Some of the different factors are: there is uncertainty in the material properties. You take a material, you test it in a lab, you calculate that the strength is 100 megapascal, but in real life the strength might be 92, 95 megapascal. There is uncertainty of loading. There might be some reckless use, or something might happen during the application which leads to slightly more or slightly less load than you were expecting. There is uncertainty analysis. While making analysis, you are making large number of assumptions. Maybe those assumptions, those calculations are not right. Or maybe sometimes there is a possibility of the load is increasing and decreasing. There are maintenance requirements. There is risk to life and property. So there are large number of factors based on which factor of safety depends on. In this course, we will not discuss how factor of safety is considered, but that if a factor of safety is given, then how to do the stress analysis. So this brings me to the end of video 4. Thank you.